In this lesson, we want to be able to say that I can find the maximum and minimum values of a function over a region. This is chapter 1.8, part 1 of optimizing linear programming. First off, linear programming is a method for finding the maximum or minimum value of a function over a given system of inequalities, with each inequality representing a constraint. Feasible regions of linear programming represent the shaded region on the graph where all the inequalities overlap. So for example, the shaded region would be that red area in this example. That is a feasible region. It's the area that all of them would overlap in this example. Vertex are the points where two or more constraints or boundaries intersect on a feasible region. So the vertex of this would be right here, right here, right here, and right here. That would be the vertex of this linear program. Then constraint is restriction that the solution must satisfy. The restraints would be these lines right here. This is the boundary that the shaded or feasible region cannot cross. We know it is bounded whenever the feasible region is enclosed by the constraints. Notice this area is stuck between this boundary. Also, something else you need to know is that where these vertices intersect, these are the points that we want to check to find our maximum and minimum value. We know that a maximum or minimum value of a related function always occurs at one of these vertices. We know it is unbounded whenever the feasible region is open and can go on forever. So notice that this boundary does not enclose it all the way. So the area goes on forever, going up in this case. We also are told that an unbounded region has either a maximum or minimum value, but not both. So one of those points, one of those vertices, will be either the maximum or the minimum value. In this example, we are told to graph the system of inequalities. We want to name the coordinates of the vertices of the feasible region. We want to find the maximum and minimum values of the function for this region. So in order to find the vertices for the feasible region, what we need to first do is actually just graph this. So we know that with y being between 3 and 5 and there being no x value, we know that this would be a horizontal line at 3. And we also know that there would be another horizontal line at 5. With this, we know that the values are going to be stuck between here, somewhere between 3 and 5. For this next part, we know that x is bigger than or equal to -3, so that tells us that we are going to have a vertical line at -3. We know that anytime it's x equals to a value or x is bigger than or equal to a value, it's vertical. So with that being said, in order to graph this, we are going to have a vertical line being at that number. To know which way to shade, what we end up doing is we end up looking and finding a value that's bigger than -3. A value that's bigger than -3 is, of course, 2. We go ahead and shade towards the 2 and the 4. Next, we're going to look at this y is less than or equal to -x plus 6. That looks like it's in slope-intercept form besides the inequality. We know that the y-intercept will be at 6. We know that slope is -1 over 1, so we're going to go down 1 over 1, down 1 over 1, and so on. And this forms a linear line. In order to figure out where to shade with this one, we're just going to choose a point. 0, 0 is always a great point to choose. 0, 0 would tell us that this is 0 is less than or equal to 0 plus 6. That is true, so we're going to shade towards 0, 0. So the system of inequalities would look like this. Cleaning this up, we are going to just look at the feasible region. In order to find the vertices, what we're going to do is we are going to look at the graph. Notice that we have a vertice right here, which is at 1, 4. We have another one at 3, 2. We have another one which is at -3, 2. And lastly, we have one at -3, 4. So these are our vertices. In order to find the maximum or the minimum value, we need to plug these vertices into our function. So we have our x values and our y values. Remember, ordered pairs always start with x and in the y value. So what we're going to do is we're going to do f of 1 comma 4. This is going to be 2 times 1 minus by 4, which is going to give us 2 minus by 4, which equals negative 2. That is the 1 comma 4. In order to find f of 3 comma 2, this would be 2 times 3 minus by 2, which gives us 6 minus by 2, and that gives us 4. In order to find f of negative 3 comma 2, we are going to end up with 2 times negative 3 minus by 2, which gives us negative 6 minus by 2, which is negative 8. If we want to find f of negative 3 comma 4, this is going to be 2 times negative 3 minus by 4, which gives us negative 6 minus 4, which gives us negative 10. So putting these together, we see that our maximum value is going to end up to be this 4, and the minimum value is going to be negative 10. So let's write that out. Max equals 4, and min equals negative 10. So our maximum and minimum values is 4, and our minimum is negative 10. And our vertices is 1 comma 4, 3 comma 2, negative 3 comma 2, and negative 3 comma 4. For this next example, we want to do the same thing. We want to find the vertices, the coordinates of those, and also the maximum and minimum values. So let's do the same thing. We have our inequality, our y-intercept is at 4, our slope is negative 2. In order to know which side to shade for this inequality, we just choose a random point. I'm going to choose 0, comma 2. 0, comma 2 is right here. It's not on the graph. So we have 2 is less than or equal to 4. And that is true. So we shade towards 0, comma 2. For this next inequality, we do the same thing. We have our y-intercept being at negative 2, and our slope is 1, 1. So we are going to just have our graph look like this. In order to know which way to shade, we just choose a point. Let's just choose 0, comma 0. That's an easy point. So 0 is bigger than or equal to negative 2. That is true, so we shade towards that region. And lastly, to graph this inequality y is less than or equal to 4, we know that this is going to be a horizontal line at 4 because we have no x value. Choose a point for y that's smaller than it. We know that 0 is smaller than 4, so we shade towards 0. Cleaning this up, we know that our feasible region is going to be right here. Our vertices are right here. We have one at 0, comma 4, and another one at 2, comma 0. Notice that the feasible region is unbounded. This means that we have either a maximum or a minimum point, not both. In order to figure out what our maximum or minimum point are, let's go ahead and just plug this into our function. So we have f of 0, comma 4, which is going to be the same thing as 5 times 0, minus by 3 times 4, which is going to give us 0 minus by 12, which is negative 12. If we want to find f of 2, comma 0, this is going to be 5 times 2 minus by 3 times 0. In other words, this is 10 minus by nothing, which is 10. Well, how do we know which one's the maximum or which one is the minimum? In order to figure out which one's the maximum or minimum point, we have to figure out if we can get anything larger or anything smaller than these values. So let's try a few numbers. Our maximum we think is 10, and our minimum we think is 12. Let's see if we can find something a little bit larger or a little bit smaller. Let's try, for example, to do 0, comma negative 2. This will give us the grand total of 0 plus 6. Well, that's not bigger than 10 or smaller than negative 12. Let's try another value. Negative 10, comma 0. Let's try this point. This will give us 5 times negative 10 is negative 50. Minus by 0, it gives us negative 50. Wait, negative 50 is smaller than what we thought the minimum was. So we have no minimum value. So negative 12 is not our minimum because this is unbounded. In this case, we would have our maximum being 10.